All right, so we start out with this day of notes, and I really want to review everything that we've talked about previously. Okay, from electron configuration to quantum numbers to our orbital box diagrams, and I want to tie it in here with this. Now, we start by looking at iron, and we're going to get to the d electrons here, but before we get to that, I want to do a couple of things. Number one, I want to write the complete electron configuration and then our shorthand notation here. Okay, so if we start with our iron, okay, if we start with iron and we write down our complete electron configuration, we would have this. Remember, this is all for iron, and what we would call the complete electron configuration would be as follows. Okay, we would have this. We would have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then we would finally get to our element iron at 3d6. Okay, now that's the complete electron configuration. If we would have the shorthand electron configuration, remember what we do to look at our shorthand electron configuration is this. We would go to the first previous noble gas. So what we would do is this. Iron is in period 4, so we'd go up to period 3, all the way to the right. The first previous noble gas would be argon, so we would put it in brackets, just like this. And we'd continue writing the electron configuration just like we normally would. And so we would end with 4s2 and 3d6. Now, I want to take a moment here and I want to go ahead and write our orbital box diagrams for this last portion of our shorthand notation. Okay, so I just boxed it in green here. And what we have here is our 4s. Remember, the s subshell is written where we have one orbital, and we're going to represent that with one particular box. Okay, so here's our one box. To identify that it's a 4s level, we would put 4s. And then before we start adding electrons, I want to put in my d subshell, which it contains 5d orbitals. And so we draw them as 5 boxes connected together. Okay. Okay, and we would label this as the 3D level. All right. Now we go back and we add our electrons. Okay, so we add our particular electrons, and I identify this. In the 4s level, we have 2 electrons to put in. Okay, so we would start out with a up arrow, and then we've used one of 2 electrons. We would add that second arrow as a down arrow. Then I look at this. The 3D level has 6 electrons to deal with. So we would start with an up arrow in the furthest left box. And then we have to abide by our rules, right? Hund's rule says, hey, each electron must have, each orbital must have 1 electron before you go back and add doubles. So we would add our second electrons as the same spin, an up arrow, in that second box or second orbital. The third electron right there in the middle with our particular up arrow again, our fourth electron, and our fifth electron. All of these up arrows, there's 1 electron per orbital. Our 6th arrow, we would go back to our original orbital, right, all the way here on the left here of the 3D section, and we would finally go back and we would add that second electron, but it has to have the opposite spins, okay? So again, abiding by our rules, drawing our orbital box diagram, each orbital is going to get an electron before you go back and you add seconds, before you add that second electron in the orbital. Now, back to this original question here of this, okay? We want to take a look at just the d electrons in iron. So I'm going to box our orbital box diagram in purple here, and we're going to look at our particular quantum numbers just for this particular D section. Now, I do want to make one important note, and that is this, okay? With our particular orbital box diagrams, just so you know, we must fill each orbital with one electron before placing a second electron in an orbital. All right, so back to this, back to our electron configuration of what I have boxed in purple. All right, so as a reminder, right, we would have our N for energy level. We'd have our N for energy level. We would have our L for the sublevel. We would have the M sub L for our specific orbital, aka the timeline there. And then we would have our M sub S to represent the spin of that particular electron, okay? Well, every single one of the electron in the 3D section is going to be in the third energy level, okay? So if we look at this first up arrow way on the left, it's in the third energy level. It's also in the D sublevel. And remember, I said each sublevel has a unique number associated with that L value. Because it's in the D sublevel, this gets a value of 2. And then here's where we start to get different. The M sub L is our number line. So our number line says, hey, way on the left, number line started right in the middle of 0. So our M sub L for this first up arrow would be -2. And then it's an up arrow, so it would be plus half to represent the spin. Okay, now I'm going to go to the next orbital, the next up arrow, right? The next box here. Okay, I'm going to skip over the down arrow just for now, and then we'll get to that at the end. It's still in the third energy level. It's still in the D sublevel, so it's given a 2. But now, again, I moved one box over. I have to abide by my timeline there, and so we would get a -1. It's still an up arrow, so we'd have a plus half. Okay. Next arrow, right in the middle, up arrow still. It's still in the third energy level. It is still in the D sublevel, so it still gets a 2, but it's in the middle box. So our M sub L is a 0. It's an up arrow, so still plus half. The next electron, going to the right again, still an up arrow. It's still the third energy level. It's still in the D sublevel, so we give that a 2. It's an up arrow in that box, almost to the right here. And so we give that a +1. It's an up arrow, so we have a plus half. And then we get to our electron way here on the right-hand side, still in the third energy level. It's still in the D sublevel, so D sublevel gets a 2. It's in the far right box, so the M sub L is a +2, and it's an up arrow, so plus half. Now we get back to that down arrow in our first orbital that we looked at. Now, it's still in the third energy level. The D sublevel is represented by 2. It's way to the left, so -2, but it's a down arrow, so we get -1/2. Now, I want to emphasize 2 more things, and that is this. Number 1, in our description of our d electrons in iron, notice how no set of 4 quantum numbers are the same, because they're describing one specific electron that we can isolate and look at and identify the specific properties. The other question is this. We've represented orbitals via boxes. So the question should be, are orbitals really shaped like boxes? Well, the answer is no. Hopefully it's pretty obvious there. But we need to take a look more specifically in this day of notes here. We need to say, okay, well, if they aren't shaped like boxes, what do they look like? Okay. And so we are going to see a definition, and we're going to see some explanations of this particular definition. All right. Now, again, this was kind of the groundwork for what we can see here. All right. So we'll add some information here. We'll continue to go through this, and we will add some info to not our orbital box diagrams, but actually specifically what our orbitals are. So our orbitals, they are a statistic probability of where we are most likely to find that specific electron. Okay, remember the quantum numbers use 4 numbers to describe a specific electron. Now we need to know, hey, where in the world is this electron going to be around the atom? Well, based upon a lot of things, probability, statistics, a lot of math and physics, we can say relatively it should be in this area. And being in that area, it's going to have a certain unique shape. All right. What happens with this is we need to take a look at the physics and the math concepts that are going to describe how we get these specific shapes. Okay. So we first start looking here at our Heisenberg uncertainty principle. You have to remember that in the 19-teens and 20s, when all this information is coming out, there's some questions. There's a lot of top-end scientists, probably some of the top in the entire world, probably that have ever even existed. And so we have German scientists here, Heisenberg, he says, okay, I cannot precisely know exactly where the electron is and the speed at the same time. I can know one or the other, but I can't know both. Okay, and he proves this mathematically. And you don't really need to know the formula, but he did have the formula here and some unique things here. You see that position and momentum, the speed here, as he describes there, and it also involves that Planck's constant. Now, we haven't really talked about Planck's constant, but we did talk about energy levels acting like stair step. Well, Planck actually quantified that number, and that's why he has that constant, that 6.626 times 10 to the negative 34. Again, a mathematical explanation for what's occurring here. So again, this proves that Bohr's model, where a electron orbits in that nice circle orbit, can't exist, because Heisenberg proves it mathematically. Okay. Then our wave function. Remember, as electrons get excited and they go up in energy level, and then they crash back down, they're going to give off energy in the form of light. Well, we knew at the time light behaved as a wave and had a lot of wave-like characteristics and a lot of wave-like properties. Okay. So what we could do here is this. We could apply this wave function, which uses this fancy looking trident symbol, I'll call it. And we could identify, based on how light's moving, where, or wave motion of the electron, right? We know about light. We can tie it to the electron because lights release as energy as they go crash to their original ground state. This is where we get our probability. And no, you don't need to calculate mathematically here, but you need to know that math supports what we're going to talk about here. So going a little bit more in depth here with our information, we can finally get to our shape of our particular orbitals, okay? And so our shape of our orbitals are determined by a few things. And I want to pause because there was one minor thing that we skipped over, and that was talking about our particular de Broglie wave model here. Okay, so we skipped over the slide. I want to make sure we have it. Okay, so just give me one moment here to add this in. And there we go. Okay, so again, orbitals, right? Probability finding it, right? What we skipped over was this right here. De Broglie. He is the one that says electrons are going to move as a wave. Okay, he proved it mathematically, again, using Planck's constant. At about the same time Heisenberg is recognizing this info and doing his own experiments, that's when we got to Heisenberg's uncertainty principle. Okay, so we should have had that de Broglie slide here. Both of those items, again, de Broglie, hey, electron is moving as a wave. Heisenberg says, great. If it moves like a wave, maybe I should know how to predict where and how fast it's going to be. He says, nope, can't happen because of this formula. All right. And this gets us to our wave function. So they combine this info from de Broglie and Heisenberg, and they are able to give our orbitals an actual shape. All right. So that's where we get to this information right here. Our shape of our particular orbitals is determined based on that probability of where we are most likely to find the electron. Remember, it moves like a wave, electron is. But Heisenberg said, no, can't know exactly where it's at and how fast it's moving. We can know a general idea, but we're not going to know both. All right. So based on the type of orbital you have is going to determine the shape. And again, all proven mathematically. And this is really an important bit of information that you know the shape of each orbital, and I can identify it as a region. All right, so S, spherical shape here. Notice here, as you increase in energy levels, your sphere is getting bigger, and that exists for all of these orbitals here. So a 2p is going to be smaller than a 3p. A 5p is going to be bigger than each of those. A p orbital is dumbbell shaped. Now, you have an X, Y, and Z axis. That's because atoms exist in 3 dimensions, right? And so we have to express that on those 3 axi that we see here. Our other orbitals, remember, we're concerned about S, P, D, and F because those are the orbitals in which we know the elements or the elements we know of exist in. And so the D orbitals, we have a clover leaf shape in 4 of them. And then we have what I call a dumbbell with a donut shape. Looks a lot like the p orbital, but then it has this ring around the center of it. An F orbital, they're really, really complicated, right? You're starting to bring in a lot of different factors. You got to remember the F orbital doesn't even come into the 4F, the 4th energy level. So there's a lot of complexity with that as well. And that's why you get such a complex shape, okay? Bottom line with this is that shapes, those shapes that we just showed you, important to identify it, they come from that knowledge that electrons are moving like a wave. We cannot predict where and how fast electrons are moving, the Heisenberg uncertainty principle, and that their shape is a statistical probability of where we are most likely to find a particular electron. Now, let's tie this all together and let's talk about, again, concept that's a little bit less abstract, some things that we can have here, okay? Electron configuration. I'm going to break them down in groups of 2 with the exception of that last one here. And I want to point out this. If I go, and I'm going to underline a few things. If I go and I underline these electrons way at the end, 2s1, 4s1. These 2 elements, they're different, right? It's lithium and potassium. They have different electron configurations, but right here at the very, very end, this is some important knowledge to identify. Both of these, are going to have 1 valence electron, right? An electron in its outermost energy level, okay? And for lithium, it's in the 2nd energy level. For potassium, it's in the 4th energy level. But both have one valence electron, okay? And both are in group number 1 of the periodic table. Okay, well, let's go to my next set here. Now, some interesting things here, right? I just highlighted one section here, but valence electrons, electrons in the outermost energy level. Well, check this out. Oxygen has the 2s, there's 2 electrons, plus 4 electrons from the 2p, total of 6. Sulfur, 3s, there's 2 electrons, 3p, there's 4, total of 6. Both of these have 6 valence electrons. Okay, so both have 6 valence electrons. Well, shouldn't be a surprise here. Both are in group 16, or sometimes we call these group 6A of the periodic table. Okay, so now let's go to these next elements here. And these next elements here, titanium and nickel. Now, again, valence electrons are electrons in the outermost energy level. Okay, well, the outermost energy level is going to be the 4s for each of these, and both of them have 2 valence electrons. Okay, so again, both of these items here have 2 valence electrons. Now, they are not in the same group, but they belong to this unique group called the D block, or more commonly called the transition elements. Okay? And now it gets us down to this one item all by itself. Okay? Well, guess what? Krypton. On the very far right-hand side, okay? Krypton is known as a noble gas, okay? So krypton here, known as a noble gas. Then I want to point out this. Valence electrons, the 4s has 2 of them, plus the 4p, which has 6 of them. Krypton, and any noble gas for that matter, krypton is going to have 8 valence electrons. Now, krypton itself would have the remaining electrons, 28 of them. 28 electrons would be what we call core electrons. Now, this leaves us with 2 options, okay? We've talked about valence electrons, and we talked about how they could be associated with different groups in the periodic table. And so electrons and atoms have 2 choices. They can either be core electrons or valence electrons. All right, so now we can start using those electrons in the outermost energy level, and we could start making sense of this to some information we're about ready to explain and have in future days of our notes, okay? And so we take this information and we get this. We get actually formal definitions here of valence and core electrons. Valence are electrons in the outermost energy level, a highest energy level, okay? Core electrons, every other electron that is not considered a valence electron, okay? Now, valence electron is going to equal our group number. And I already described group number 16. Technically, it's 16 minus 10 is the number of valence electrons. Sometimes we will identify that particular trend. The other thing is this. If an element is in the same group, it's going to have the same valence electrons, and it's going to have very similar chemical properties. So here is this. Valence electrons are going to be a major factor in how an element or an atom reacts in a particular chemical reaction. Now we get to this. Why 8? We said that krypton is a noble gas and it had 8 valence electrons, 28 core. Why 8? Well, noble gases. The reason we call them noble is that they're relatively unreactive. They have 8 valence electrons, which fills the outermost S level, S subshell, and the outermost P subshell. That essentially satisfies an atom, and it doesn't want to gain or lose electrons, which means it's not going to be involved in hardly any, almost none, chemical reactions. Okay? It gives that atom stability. And so we get to our octet rule. And so that's this, that atoms are going to gain, lose, or share electrons in order to get to that 8 valence electrons. The exception to this rule is helium. Helium only owns 2 valence electrons, same thing with hydrogen, okay, that group 1 there. But again, if there's anything that forms a noble gas electron configuration as helium, doesn't abide by the octet. Everything else wants 8 valence electrons. It's filling the outer S subshell, and it's filling the outer P subshell. So let's finish out with a couple of examples. All right, we got neon, which is our noble gas. Okay, then we got sodium, which is in group number 1. Now, sodium, I want to point out this. Sodium right now, it is uncharged, which means that we have this. Sodium itself, right here, sodium itself is going to have 11 protons, and it's going to have 11 electrons. So it's neutral. But it wants to be like the cool kids club, the noble gases. Okay? So as a result of this here, our sodium is very reactive. Why this is because it does not have noble gas electron configuration. And what it wants to do is it wants to be like the cool kids club, wants to be like neon. All right, so it wants to lose 1 electron. It wants to lose that 1 valence electron. It wants to lose that 3s level. So it reacts and it loses that 3s electron, right? You could say, all right, it reacts. It loses that 3s electron, and as a result, it now has the electron configuration of 1s2, 2s2, 2p6. Now, that's going to match the electron configuration of neon, but I want to make a couple of essential points, and that is this, all right? Sodium still has 11 protons, because the moment you change the number of protons, you change the identity of that particular atom. You would no longer have sodium. However, it lost 1 electron, which has a negative charge. You could think of it as minusing a -1. And so now it only has 10 electrons. Okay? And so I want to make a couple of key points here. And I'm going to start out here with the electron configuration that sodium has by just losing that 1 valence electrons. Number one, it now has, by losing 1 valence electron, it has that noble gas electron configuration. All right, well, that really satisfies sodium. It doesn't need to react anymore, and it's happy. Okay? The other key point, just because it has a noble gas electron configuration, it does not make it a noble gas. it simply has the electron configuration that matches that of neon, that noble gas there. Okay? And so I want to take a moment here and now talk about the difference in the number of protons versus the number of our particular electrons. Okay? And so I go into this. Okay? I go and I want to highlight this info right here. Number one, it now has more protons, more positive things than electrons. So this is going to have a net charge of +1. As a result, we no longer have a sodium atom, but we have a sodium ion. And that sodium ion has a net charge of +1. We simply write that as 1 plus in our area. Okay? Now, this is referred to as now, because it's charged up, not a sodium atom, but a sodium ion. And I also want to make this point here, that because it's an ion and it's satisfied, it's like I obtain that noble gas electron configuration, it's no longer reactive. Okay, so the final point that I want to make on this particular scenario, this example here, is this. Well, okay, how exactly did sodium obtain this noble gas electron configuration? Well, it's going to find a way of losing that one valence electron that it needs to through a chemical reaction. All right, so now let's take a look at another example. We won't go as in depth because a lot of the knowledge can be transferred. We're just going to highlight some important things. Okay, so we go to the next example. We still have neon as our noble gas, the noble gas electron configuration that now fluorine wants to obtain. Okay, so a couple of things that we need to emphasize is this. At this current state, our sodium here has no net charge. Right now, our fluorine has 9 protons and it has 9 electrons. Okay, so at this current state here, this atom, this fluorine atom, has no net charge, but it wants to be like the cool kids club. It wants to be like that closest noble gas, and it wants to gain simply just one electron. How is it going to do it? I'm not going to write this down again, but it's going to obtain that one electron through a chemical reaction. All right? When it gains that one valence electron, here, we add that one valence electron through a chemical reaction, right? It just doesn't pull it out of thin air. It gets the now electron configuration as 1s2, 2s2, and now 2p6. Okay? Well, again, we have to identify this. As it gained that one valence electrons, it's not going to affect the number of protons. It's still going to have 9 protons. However, this time it's going to have 10 electrons. So if we talk about this portion right here, now through a chemical reaction, by obtaining one additional electron here, it now has a net charge of -1. And as a result, it's no longer a fluorine atom, but it is a fluoride ion. Okay? Now, remember, with an anion, a negatively charged ion, the name at the end is going to have that IDE to reflect that negative charge. Okay? And so we end here with just a few more things. Okay? We end with this. Our trends can be directly looked at on the periodic table, and we can associate valence electrons with the octet rule and with the charge that each element, each atom in that group, family, up and down column, is going to have with our periodic table. So let's take a moment here. Now, nonmetals gain electrons. You are adding a negative substance. You're adding a negative particle. So you're going to be negatively charged. Metals will will lose an electron. You are subtracting something with a negative charge, minusing a minus, and you'll get a positive cation. All right? So let's do this. Our last two things that I want to go over. If we look at our valence electrons, okay, our valence electrons. So first off here, I'm just going to show you, I abbreviate valence electrons as VE. Well, group number 1 has 1 valence electron. Group number 2 has 2 valence electrons. For the most part, the transition metals have 2 valence electrons. There is some exception, same thing with the intertransition metals, but I'm just going to skip over those for right now and get to group number 13 with boron. They have 3 valence electrons, 4 valence electrons, 5 valence electrons, 6 valence electrons, 7 valence electrons, and then our noble gases will have 8 valence electrons. Now, where I wrote this, the whole group. So, for example, our noble gases, helium, all the way down to the most recent element found, number 118, all of those elements have 8 valence electrons. For example, group number 2, beryllium, all the way down to radium, all of those have 2 valence electrons. Same group, up and down column, going to have the same number of valence electrons. based on that, that will help determine our charges. All right. So I want to make this statement here with our charges here, and that is this. With our charges, each group will form the same ionic charge because they have the same number of valence electrons. All right, so to end this here, group 1, sodium, we saw this, right? Group 1, when it forms an ion, it's going to form an ion with a +1 charge. Group 2 will form an ion with a +2 charge. Group 13 with boron had 3 valence electrons. It's going to have a +3. Now, group with carbon. Carbon starts our top of the mountain, I'll call it. This could form a plus or minus 4 charge. Group 15, they have 5 valence electrons. They need to gain 3 valence electrons, so they would have a -3 charge. Oxygen's group, a -2 charge, and then fluorine's group, a -1 charge. Okay, I don't put a charge up here for the noble gases because they already have that quality number of meeting the octet rule, and they're filling the outermost S and P subshells. All right, a lot of information, a lot of stuff right here at the end that's very, very applicable and very, very identifiable in terms of what we can use to help describe our chemical bonding here in the next few days of notes.